Start the meeting. I will go to share screen. Okay, so I want to talk about error detection. Oh, it is acting up.
Oh, I thought it was just fun.
I mean, some of it is fine, but
I detect an error.
yeah.
You did that on purpose.
Yes. Of course I did this on purpose, yes. So I'm actually giving a talk on this at MathFest in a little bit. And when I sent this to the organizers, they then passed it on. And so I said, wait a minute, oh God, there's a bunch of typos, let me fix it. And then once they fixed it, oh, wait a minute. So they realized in time that yes, I did mean to deliberately misspell everything, or almost everything. I'm assuming nobody has trouble figuring out what the title of the course, or of the lecture is.
So when you say, oh, my computer is really acting up, everybody thinks that it is really serious?
Yes. And my previous computer was acting up, and it had an interesting feature where it would just turn off randomly.
Oh.
And so anyways. Yeah. I sent it back to Dell, and they said that there was some water damage. I don't know how, but that's what they said. So what I want to talk about is two parts, error detection and error correction. So the detection is often the easier part, to know that something is wrong. The correction is the harder part. What is the most efficient way to fix what you have? So we've talked about this many times. In fact, we were talking about this a moment ago, which is what was leading me to segue into here. It's enough to just send strings of zeros and ones. So if we're doing just 5 digits, we can send 00000 to 11010 for the Z. The two major issues which we've talked about is we want to transmit messages so that only the desired recipient can read, and we want to ensure that the correct message is sent. And that's what we're going to be talking about now. So earlier, we were talking about the first part, the transmission. So that's why these slides probably look familiar. Originally, I was going to do this part tomorrow. Since we've all been doing this right now, I'm going to go through this really fast. We were talking about what happens if just one digit is mistransmitted, if we send an 8 there rather than a 7, and we see the messages aren't even close. And this is one of the huge advantages of RSA, is that it bundles things together, so you don't have to worry, well, if I'm close, is that enough to get a sense of what you know? No, close is not good enough. All right, so we're going to concentrate on error detection and correction. So the first part is just detecting an error was made. And there's a lot of ways to do this. I'm going to first talk about the check digit approach. So if it's easy to read something again, then it's enough to just detect that an error was made. So in my mind, one of the greatest inventions in the 20th century is the scanner that they use at supermarkets. The ability so that you do not need somebody to know all the prices or to have this big book, because things are always changing in front of them, to figure out how much to charge you for this. They just scan the item and they charge you for it. Not only that, but it immediately updates the store inventory. So you no longer have to pay people to be going down the shelves and keeping track. And when you reach certain critical thresholds, it then puts in orders to the stores, warehouses. We need to be resupplied in this. Even better, it can start doing some analysis of your purchasing habits. And data like this can be mined for a bunch of tremendous applications. So one of my favorite examples is there was a Target store in the Midwest which sent a family some coupons for baby products. And the father was a little bit upset about this because he and his wife are well past the age of having children. His high school daughter and junior high school son are too young. Why are you bothering me with coupons like this? And the manager's very apologetic, very, very sorry. Here's some complimentary coupons, gift cards on the house. We're very sorry. A few days later, the manager calls back the father to make sure everything is okay and to apologize once again. And the father has to be a little bit sheepish and admit that there were certain extracurricular activities being engaged upon that he was unaware of. And that those coupons for baby products will be useful for his daughter in the very near future. So Target knew before he did that he was going to be a grandfather.
Wow.
How did they do this? Well, certain products are correlated with each other. And people who tend to buy stuff like this are likely to. And what stores want to do, especially if you have new kids, and I know we have at least one person who I think would fit in this category, you want to maximize your effectiveness when you're shopping. If I can go one place and get the baby toys and get the food and this and that, that's valuable. So they want to give you coupons to draw you into the store. Now, most people don't like to feel like they're being targeted. They like to feel that they're special. Given that the fact that the name of the store is Target, I'm not sure how reasonable of an expectation this is. So they had a very clever solution to what to do in this situation. They still want to target the people, but they don't want people to feel like they're being targeted. So what they did is they put in coupons that were anti-correlated with your purchasing habits to make it look like it was a completely random set of coupons, with possibly the coupons that they want you to see in strategic locations that are more likely to be seen. But if you now look at all the coupons, it's all like, wow, they really know me. They're deliberately throwing in some things to make it misleading. Just like if you're ever doing a search for something, once you find it, if you want people to know what you're looking for, you never stop on that. You always do a few more things to have a trail to confuse people. So there's a lot of great things that you can do with these scanners in supermarkets. And so has anybody ever been in a supermarket where they've scanned a product and it hasn't gotten the correct value, it has been able to read the barcode?
Yes.
And then basically at that point, your life is over, there's nothing you can do, you can't have the product, right? No. What do?
You take it back to the customer office.
No, you don't go back to the customer office. You scan it again.
Oh.
And normally on the second time it works. So if you're in a situation where it's very easy to redo the process, you don't need to have an error correction. You just need to know, hey, a mistake was made, let's try again. If you're in a situation, let's say you happen to command a nuclear submarine and you're on station. You surface only at key strategic times, agreed upon in advance to receive signals. You can't keep going back and forth and getting the message again. You've got to get it right on the first try. So in a situation like that, it's not enough to know, 10 minutes later, Captain, we're having trouble decrypting. Where were we supposed to nuke? Well, what do you think it was? Well, you need to know. You can't be doing the correct, you can't be saying, well, just transmit the message again. So the first stuff we're going to do is designed for situations like the scanner, where it is very easy to just redo it. So scanner at a supermarket. So what we're doing here is, for the rest of the day, everything in pink is going to be the data, the stuff I care about. Everything in blue is going to be the check digit. And because people have different accents, I will do it for the people who speak base 10 and the people who speak base 2. For those of you who like jokes, there are 10 types of people in the world. Those who understand binary and those who don't. Okay? And so the way the check digit works is you add up all of the numbers and then you put as the check digit what you need to make the sum 0 mod your number. So here I want the sum to be 0 mod 10, I want it to be a multiple of 10. Here I want it to be 0 mod 2, I want it to be a multiple of 2. So since I have 1, 1, 0, 1, this adds up to 3, which is odd, so I add 1, and now it works. Over here, 9 plus 1 is 10, 17, so I add 3 to make it 20. Because I'm adding just a number between 0 and 9 or 0 and 1, there will be a unique number that always works. And now what's nice is imagine you receive these as messages. Is it possible for either of these messages to be correct? No. Why can't either message be correct? Yeah, so if I try to sum all of this, I get 21. If I sum this, I get 3. This is not even, this is not a multiple of 2, this is not a multiple of 10. So a mistake was made. Unfortunately, I don't know where the mistake is. The mistake could be in one of the data digits, or it could be in one of the check digits. Because I have 2, I have the ability to do both. So here it's 9, 1, 3, 4, 3, 9, 2, 3, 4, 3. Okay, so knowing what the correct answer was, I know that the error was made here. The second one was 1, 1, 0, 1, 1, 1, 1, 0, 1, 0. Okay, so there it was with the check digit. So the problem with this method is it detects that an error was made, but it doesn't tell you where. And so this led to a huge industry of trying to not only detect where errors were made, but correct them. So a lot of the subject is due to Hamming. And the funny story that's often told is because when he was starting out, he was low person on the totem pole, his programs got to run at night. And he would come back, he would get to do it over the weekend, he'd leave the stuff on a Friday, come back on a Monday, and he would find it ran 16 lines until there was an error. And then being low person on the totem pole, you wait another week, gets to run on the weekend, it does another 18 lines. And your modulo some expletives, it was, if that blessed computer can detect that an error was made, why can't that blessed computer correct the error that was made? And so it inspired him to come up with very efficient ways to transmit information and to recognize when an error is being made. So there's more involved systems you can do. This is just one of many links where, what if you transpose 2 digits? If you go back to what we had a moment ago, if I transpose the 1 and the 3, or the 0 and the 1, the check digit is still going to work, and I can't detect an error like that. If you think about people typing on a keyboard, the is probably the most common 3-letter word. TEH is also very common. In terms of just how you're typing, the H sometimes comes after the E. And so transposition errors are extremely important. And so there's a whole slew of very elementary approaches that allow you to detect certain types of errors. It doesn't allow you to correct them, but at least allows you to know what kind of errors have been made. And so, there's a link to one thing here. If you do a little bit of searching on some of those algorithms, you can find plenty more. And then all of these slides will be online. I have them off of my home page, and I will be emailing Midge the links that she can then share with everybody. So we want to detect where the error is. So one solution is to tell me twice. So we agree that we will only transmit 1, 1 or 0, 0. And if we agree to only transmit 1, 1 or 0, 0, then if we receive 0, 1, we know an error was made. We don't know what the error is, but we know an error was made. Is it possible to get 1, 1 and have that be an error? Yes. It would be a double error. And the hope is that a double error is rare. That if you are communicating with somebody, the hope is that most of the time, your message is being transmitted correctly. If it's not, you may have issues in the communication. If you had to choose a probability for the successful transmission of a digit, what would you choose?
3.
As the probability of the successful transmission of a digit? Yeah. 1, right? If you had this magic wand and you could create a system that would be 100% effective, you would do that. In which case, we wouldn't need to do this lecture and we could go out and start drinking. We don't have that magic wand. What is the worst percent for successful transmission?
0.
No. 50. So who is a Seinfeld fan? Not that many. All right. There is a Captain Seinfeld named George Costanza, and if you Google loser, you might actually see his image. He's a person who has not had a successful life. And there's one episode called The Opposite where he's bemoaning to his friends how every decision he's made is wrong. And so later here, I actually do have the links to that episode. I actually played them to the 60 kids in the math club at my elementary school, and they loved it. In fact, I got a few new Seinfeld fans from this. And so he's going on and on about every time I've made a decision, it's turned out to be wrong. So one of his friends says, well, George, if every choice you make is wrong, then the opposite must be right. And he starts doing the opposite, including going up to an attractive woman and saying, hello, my name is George, I'm unemployed and I live with my parents. He goes, hi, I'm Victoria. What? He ends up getting a job interview with the New York Yankees. And Steinbrenner walks in the middle of the interview, the owner of the Yankees, and says, it's nice to meet you. And he goes, I wish I could say the same to you, but... and gets the job for being the only person willing to speak his mind. Now, it is extremely important, if you want to use this method in your life, that you are in a binary world where there are only 2 possibilities. One is right and one is wrong, and you know that you're always wrong. Most of the time, there are more than 2 alternatives, and we don't know that we're always wrong. So this is why the worst probability of successful transmission is actually 50%. Because if it's 50% and if you receive a 1, well, if I have a 50% chance of being right, it's equally likely to be a 1 or a 0. 50% is the absolute worst. 0% is effectively as good as 100% if you know that you're always wrong. So this is the tell me twice method. All right, so tell me twice is nice, but it doesn't tell you where the error is. So The solution is actually very simple. It's the majority rules. How many of you have seen the Tom Cruise movie Minority Report, based on a Philip K. Dick story? So in that, you have 3 sources that must all agree. And if they all agree, then you trust them as being right. And if there's a disagreement, if 2 out of 3 agree, then you will assume it's right. Although maybe there is some complicated reason as to why they're agreeing or whatnot. And so the movie involves some nice math concepts. So tell me 3 times detects and probably corrects an error. So if we assume that we have at most 1 digit that's wrong, and we promise that we're only going to transmit 111 or 000, then we're in really good shape. If we now receive 101 or 100, we know these are wrong. Because we've agreed ahead of time that we're not going to transmit anything other than 111000. So we know neither of these can be right. If the chance of making an error is small, if 2 things are telling me 0 and 1 thing is telling me 1, I'll go with the 2. And if 2 are telling me 1 and 1 telling me 0, I'll go with the 1. So as long as you make at most 1 error, tell me 3 times not only detects, but corrects the error. So this is wonderful. What's the problem with this?
Takes a lot of room.
Yeah, you can see that there's a lot more dots for slides, right? And if this was the end-all be-all, we'd stop here. So how much of your message is data? And how much of your message is designed to detect and correct errors? So what fraction of your message that you transmit is actually information? I'm sorry? A third. This is why I'm color coding, right? This is the data bit, and then we have to transmit 2 check digit bits with it. So only 1 out of every 3 digits is effectively transmitting information. I don't see any child prodigies here who are 15, 16 years old. So I'm assuming all of us remember the old dial-in modems and how long it would take to get, oh, exactly. So back then, the transmission time was extremely important. Anything you could do to cut down on that was absolutely essential. I record all of my lectures now, and I post all of my classes freely on my webpage. I was giving some talks in Boston to elementary and secondary school teachers, some of it actually related to stuff like this. And I went back to Williams to upload the files. And the lectures were on the order of like 3 gigabytes, 4 gigabytes each, and normally took a couple of minutes to upload. It uploaded almost immediately. It's spring break, the students are off campus right now. And it was amazing how noticeable the difference was when the students weren't present in terms of the upload time. So over here, the question is, how bad is this? If you have the ability to transmit messages really fast, you might be willing to live with only 1/3 of your message being data, if transmission is so cheap. Who here remembers the 5 1/4 floppies?
Oh my God.
I'm always excited when something I'm doing exceeds 1.4 megabytes. Was that what was on the harder ones, the 3 and a? Yeah, because then I know it's more than a disk, right? So back then it was really expensive. You actually had physical copies of manuals for books, for our programs. You would have, here's the Wolfram manual, or here's the Microsoft Word manual. Nowadays, memory, disk space is essentially free. The cost of that is so small, you can just store all that stuff. So when you're trying to decide what are the issues, what do we really care about, this may not be a tremendously important issue. That said, it offends me to only have 1/3 of my message being data. What do you think the bare minimum must be to be socially acceptable, or to be mathematically acceptable? What fraction?
Less than 50%.
Less than 50% should just be right out. If you can't have at least half of your message being data, then that's just wrong. I would prefer to be at least above 50%. Depending on how much work it is, I might be willing to live with 50%, but anything below 50% is offensive, and we need to do better. So These are the clips to the Seinfeld episode. We've talked about what's wrong with the method. Only 1/3. We need to do better. So let's do tell me 4 times. Nope, that's going in the wrong way. Yeah. Now instead of having only 1/3 of the message being data, we have only 1/4. So given the failure of tell me 4 times, we can continue to tell me 5 times and tell me n times, and we see it gets worse and worse and worse. Now, we become more and more sure that the message we receive is what was intended. So, there are trade-offs. While we have less efficiency in transmission, we have more confidence in the result. And depending on what you're doing, you might want to have that confidence. Do we nuke the right target? Do we fly to the right city? Do we hire the right person? So we've decided 50% or minimum, at least 50% is going to be a success. So I want to revisit the tell me 3 times, and then we'll be getting to a point where I think it'll be good to stop and assign homework. Is this about right in terms of timeline for the day?
Yeah.
Okay. So here is 2 different ways of telling me 3 times. I can write it in a line like this, or I can write it in a triangle like this. And then the question is, why would I want to write it like this? Well, I want to try to think how to generalize. And so we saw earlier today, when we were looking at how many numbers are relatively prime to PQ, when they're distinct primes, is it's P minus 1, Q minus 1. If I expand it out as PQ minus P minus Q plus 1, that gives me some idea of how to interpret where it's coming from. PQ is all the numbers I have, subtract multiples of Q, subtract multiples of P, and then add 1 for the number that we removed twice. So the blues are always checked digits. So if I write it like this, I can view this as a check digit for the horizontal. And I can view this as a check digit for the vertical. And now imagine that we make a mistake. Imagine that there is an error in this digit here. Well, if there's an error here, this sum will not be correct. So we'll know that there's a mistake in this horizontal. And we'll know that there's a mistake in this vertical. And because we're assuming that there's only one error, if there's a mistake in the horizontal and a mistake in the vertical, I did the hands the wrong way, the only place that they intersect is that one point. And that allows us to determine where the error is. Imagine that the error is here. There will be an error in this row, but this column will be fine, so the error has to be here. So this is another way to view the tell me 3 times. And this gives us an idea of how we can do maybe transmitting 2 pieces of information. So I'm viewing it as a horizontal and a vertical check. So if I want 2 pieces of data, I can just go here, and here is my checksum for the first, and then there are my 2 checksums for the second. And then the question becomes, and I'll stop here, and this is what we'll leave for the discussion next time. What if you had 3 pieces of information to transmit, or 4, or 5, or 6? What's the best way to do? And I'm deliberately keeping the question vague. So you'll think about how you might want to transmit. And we saw when we looked at multiplying matrices, and we saw with various other things, that sometimes it's very nice to have powers of 2. That for certain problems, certain partitioning makes the analysis, makes the algebra easier. So over here, maybe it's not great to go from transmitting 1 piece of data to transmitting 2. Maybe 3 would be better, or 4, or 5, or 6. Maybe there's a better geometry we can use. Now, how efficient is this? How much of our message is data? 40%. So it's a failure, but it's not a horrible failure. If we wanted to do 3, one possibility is to put a 3rd piece here, and then a 4th, and then a 5th. And if we do it like that, we can get arbitrarily close to 50%. But we'll always be just a little bit below, which is why it's very careful to say anything below 50% I consider a failure. The other thing is you're getting a higher percent, but at the cost of transmitting a larger and larger block. And since you're only assuming that there's 1 error per block, well, the bigger the block you send, the more likely you are to have multiple errors. And so we have to be extremely careful that if the block gets too big, now we have the possibility of having 2 errors. And there are algorithms that will allow you to detect 2 errors, but there's obviously going to be more involved. So your goal for tonight is to think, what could you do if you want to transmit 3, 4, 5, 6, 7, 8, 9, whatever. And just what kind of geometries, how might you choose to arrange things? The slides are online. You obviously do not go and just look at the slides. Just try to explore and see. And the reason to do this is you might actually find something better than what we're playing with. Yes?
Can I make sure I understand this
Yes.
picture? So the 2 red dots are your actual message, and the 3 blue are data. And the 3 blue are supposed to be your
Right. So if I have 1, 0,
right.
and I wanted to fill this in, the first one would become 1, 0, 1,
Okay.
and then this would become 1, 1, 0, 0.
Okay.
So that would be the message I would want to send.
Okay.
If instead I receive 0, 0, 1, 1, 0, I now look and I see the first row sums to 1. It should sum to 0. So there's an error somewhere here. So one of these 3 is wrong. I don't know which. Now I look at the first column, it sums to 1. So one of these 2 is wrong. And the second column, both are correct. So now I know this can't be wrong. And the only intersection, the only thing that's involved is this one here. So this 0 has to be a 1. So that's the power of this method, is it allows you to figure out where the error is and to change it. And again, what's nice is because the only things we're transmitting are 0s and 1s, if you know it's not a 0, you know it's a 1. If you know it's not a 1, you know it's a 0.
So over here, 2 are data and 3 are checkbooks.
Correct. So it is still a failure in that it's below 50%. So the first thing is, can you come up with a system where you can transmit at least half of your message as the data you care about? Then can you do better? Can you transmit more than half of the message being data? And what's the best way to do things? And what I'm in the process of doing with some high school students is, this is inspired by some conversations with Jim, is to try to say, well, depending on what points we have, what might be the best configuration? And I'm trying to be extremely vague because I want you to be free in how you look at things. If I put on blinders, anybody who's ever written an exam, if you want the student to get the problem right or wrong, it's just how you break it up into parts and what you ask them. If you want them to be, I have part A, part B, part C, part D, part E, with giant flashing signs, hey, use A down below to get B, use B down below to get C, et cetera, like that. You can guide people to get to the answer. But then they'll get to essentially just following your line of thinking. I want to try to give you almost no guidance in what to look at and what to try, so that maybe you will find something very new and novel, and that could be a fun thing to discuss.
Good.
Right.
Before we head back, do I have all the emergency sheets? Does anybody not give me theirs?